Hi everyone, so welcome to my channel. So today we are going to proceed with our discussion of functions, and this section we are going to now look into detail the types of functions that were mentioned in our first discussion of functions. So today we are going to then provide some formal definitions of these three different types of functions that were mentioned, and then see how to answer some problem that are associated with these. You see. So from last time, we recall that we mentioned three different types of functions. We mentioned that functions can either be injective, which we also said stands for 1 to 1, and also functions can sometimes be surjective, meaning they're onto. Then sometimes functions can be bijective. So today we want to then understand what is the meaning of all these things. What does it mean to say a function is injective? What it means to say a function is surjective? And then finally, what it means to say a function is bijective, like that. So the first thing that we're going to look at now is injectivity. So let's understand, what does injectivity mean? So a function f, see that? So a function f whose domain is A and his codomain is B, or whose range is B, is said to be injective if f of A equal to f of B implies A is equals to B for all A, B elements of A, like that, you see. So this is how we formally define an injective function. You see that? So we say a function is injective every time when you assume that f of A is equal to f of B will always result in A being equal to B. So every time when this leads to that, then we say a function is injective. Or sometimes you can also use the negation to define a similar thing. You see that? So a function f from A to B is said to be injective or an injection if A not equal to B implies that f of A is not equal to f of B. You see. So these definitions, they are quite formal, and for someone who is new to abstraction, they can be quite tasking to assimilate. But we shall see exactly, or try to unpack what it means. You see that? So what this definition are trying to imply is that for a function to be said it's injective, one way it can qualify is that every time when you assume that this is true, and the assumption of this thing being true leads to the following result, then that's when we say that a function is injective. Or in some cases, if maybe you assume that this is true, and this being true will always lead to the following result, then we also say that a function is injective. You see that? So let's try to understand then now what it means in terms of arrow diagrams. What does it mean to say a function is injective? You see that? So using simple arrow diagrams, this is something that is easy to represent. So using the language of arrow diagrams, it means if you have some object here which I'll represent as dots, and here I represent as crosses. Or suppose now we have a function which is defined as follows, which takes these and maps them to that, which take these and map to that, which take these and maps it to this, which takes this and maps it to that, which takes this and maps it to that. So let's say this is our function. So every time when you have these kind of situations, this is an example of what we mean when we say a function is injective. That's what injectivity means. So what it simply says is trying to tell you that you can't have two arrows coming from different elements meeting at the same point. You see that? So each and every element in the domain must be uniquely paired to a unique object on the other side. So when this is the case, this is what we mean by injectivity. So this is a diagram which depicts what we mean when we say a function is injective. You see that? What about when a function is not injective? How will things change? So for a function which is not injective, this is what you're going to see now. So again, you will have your objects here which I'll represent as dots. Then you will have some object here which we'll put using crosses. So for a non-injective function, this is what you will come to see. So you will have something like this. So now when you can look at these two objects that are shown here, this object and this object, you will see that they sorry, I highlighted the wrong one. So it is this object and this object. So yeah, if you look at these two objects, you will see that they all share the same diverging point when we go to the other side. So this is an example of a function which is not injective. You see that? So injectivity requires a one-to-one correspondence. So every time when now we have many things mapping to one object, then this is no longer an injective function. So for a function to be injective, this has to be the case. You see that? So now, since we have understood exactly the formal definition of injectivity and what it means by portraying this using arrow diagrams, let's see then what kind of questions can one get in association with this concept. So one of the problems that one can get can be as follows. You see that? So given the function f of x, which is equal to 3 to x minus 1, show that f of x is injective. You see that? So you can be given a question like this one, and then you can be asked to show that this function that we have here is injective. So how can one go about answering such a problem? You see that? So to answer a problem as this one, this is how one can proceed. So at first you can recall that every time when you want to show that a function is injective, first you have to assume this is true. So you have to assume that f of x1 is equal to f of x2. Then you have to show that the assuming that this is true will always lead to x1 being equal to x2. So if you always assume that this is true and your assumption leads you to that, then you have actually showed injectivity. You see that? So since now we know how we're going to go about this, let's proceed. So what we're going to do now is I'll continue and say, suppose x1 and x2 are in the domain of f of x, because functions, they can only take arguments that are part of their domain. So I will assume that I have two things, x1 and x2, which lie in the domain of f of x, with x1 not necessarily equal to x2. You see that? So this is what I will assume for now. With the x1 and x2, they are not necessarily the same, but we want to see exactly what is going to happen under this. You see that? So assume now that, let's assume now that f of x1 is actually equal to f of x2. So if we assume that f of x1 is equal to f of x2, what does that mean? Remember, f of x1 is given as 3 to x minus 1. So this means 3 to x1 minus 1 is equal to 3 to x2 minus 1. Now, it follows from here, if we cancel these ones, that 3 to x1 is equal to 3 to x2. So if you want, you can introduce some exponents which will give you some logarithms which will give you that this is equal to that. But now you can divide both sides by this, so therefore we see that x1 is equal to x2. So therefore we can see now that since f of x1 equal to f of x2 implies x1 is equal to x2, we have that f is injective. You see that? So we can see now that from this definition that we have, this is exactly what happens. So which shows that this function that we defined here is an injective function. Or sometimes you can use the other definition, but using the other side can be very tricky, and I'm going to demonstrate it. You see that? So I will say, suppose x1 and x2 are elements in the domain of f. And then I will say, assume also that x1 is not equal to x2. Then what follows? You see that? So we can see that if x1 is not equal to x2, it follows simply that 3 to the power x1 is not equal to 3 to the power x2. Because if two numbers which are the same are raised by different powers, obviously we expect different outcomes. So again, it means if I subtract 1 from both sides, this still must not be equal to 3 to x minus 1. But if we can recognize these things and compare to the definition of the function given, you will see that the thing on the left-hand side is none other than just f of x1, and the thing on the other side is none other than f of x2. So we can see that therefore x1 not equal to x2 implies f of x1 is not equal to f of x2. Therefore, f of x is an injection. You see that? So this is how we get to prove if a function is an injection or not an injection. So let's do maybe one more example again, just to make sure that we get to understand what's going on here. So the next question again that we have is as follows. So given the function h of x, which is defined as 3 over x minus 1 plus 4, show that h of x is injective. So now I'm not going to do this problem using the two definitions. You see. So at first I'll say suppose x1 and x2 are in the domain of h of x. So suppose also that this x1 is not equal to x2. You see that? So let's suppose also that this x1 is not equal to x2. So we now know that if x1 is not equal to x2, even if I separate things, the resulting thing must not be the same. So x minus 1 must not equal to x2 minus 1 if these two are different. You see that? So which means even if I take reciprocal, 1 over x1 minus 1 must never equal to 1 over x2 minus 1. So if these things are not equal, it means multiplying by the same number also will still remain, these two things will still remain unequal. So if I multiply both sides by 3, I'll get 3 over x1 minus 1 is not equal to 3 over x2 minus 1. Then again, if I come here and add 4, since two things are equal, adding the same quantity does not affect that. So 3 over x1 minus 1 plus 4 can never be equal to 3 over x2 minus 1 plus 4. But if you look at what we have created here, we can see now that what we have here is just f of x1, h of x1, sorry, implies h of x1 is not equal to h of x2. So thus, we can see that x1 not equal to x2 implies h of x1 is not equal to h of x2. Therefore, h is an injection. You see, so that's what we mean by injectivity. So every time when you have a function which is injective, that's what it means for a function to be injective. So now, what you should pay attention to is that the x1, they are playing the role of the a and the b's that I used in the definition. You see that? So you can either use a or b if you like, or you can use x1, x2, it's up to you. The only thing is you just have to learn how to use the formal definition of injectivity to verify if a function is injective or not. You see? So what we just have to do is to look at more problems and see if we can practice playing around with this sort of manipulations to prove injectivity. You see? Now, let's look at the next type of function, which is surjective functions. So how can we prove then surjectivity now? You see, so a function f from a to b is said to be a surjection or surjective if for all b elements of b they exist an a element of a such that f of a is equals to b. So this is also a definition which is too formal. So let's try to unpack what exactly does it mean to be surjective. You see that? So in order to illustrate that, we are going to make use of our usual arrow diagram. So let's see now what it means to be surjective. And I'm going to draw a diagram which shows a function which is surjective and one which is not. So here on this side, I'll draw a function which is a surjection. And then let's draw another function which is not a surjection this side, so that we can compare what it means to be surjective and what it means to be not surjective. Yeah, so okay, so now we have our both our examples. So this is a surjective function, and what we have here is a function which is not surjective. Now, what are the differences now? What is it that what is exactly a surjective function? So a function is said to be surjective if it is the case that each and every element that lies in the range is associated with some arrow coming from the other set. You see that? Sorry. Now, here I forgot. Let me remove this. Yeah. 3. Something is fishy. What happened? Oh, sorry. I see what is my mistake now. So I draw 2 arrows to come from the same thing, which was not supposed to be the case. So this was supposed to be like this. Then we have an arrow going like that. Yeah. Yes, that's what it is. Yeah, so we say a function is surjective when each and every element in the range is associated with some arrow which comes from the domain set. Like, for example, if you come here on this side, you will see that there is this element here which resides in this set, in which there is no arrow which is coming from the other side. You see that? So every time when there is no arrow in the domain set which takes us back to the domain, then we say a function is not surjective. So a function that is surjective, it has to be the case that for each element in the range, there exists an arrow that can send us back to the domain. So if this is not the case, then a function is not surjective at all. You see that? So it is not surjective at all. For surjectivity, every element in the range must be associated with an arrow. You see, that's how things should be like. So for some labeling, so we always refer to this as the A and the B, and then this is here the playing of the A and the B. So every time when this is the case, then we say a function is a surjection for the top left hand side, but for the bottom right, this is an example of something which is not surjective. So that's what this formal definition is trying to define to us. That's why it says for all. You see that? So for those who don't know this symbol that is used here, so this symbol that is like this, it simply stands for all, meaning everything. Then when you see something like this in maths, it means they exist. So these are some symbolism that you have to make sure that you get used to, as they are used quite often in math. You see, so for all is written like that, then they exist is written like that. You see that? So what it means is that for each thing that lies in B, where B stands for the range, there must be an A such that a function can be able to send A to that B. You see? So that's what we mean by surjectivity. So surjectivity is something that at first year level we don't care much by proving if functions are surjective or not. So you can survive quite well with even if you do not know how to actually prove if a function is surjective or not. But what I'm going to do now is I'm going to give a demo on how exactly can you answer if it happens that you're asked a question like that. You see. So a typical question will be, show that the function f of x equals to e to x is a surjection. You see that? So answering these type of questions can be very tricky, especially if you do not know the logic behind it. But I'm going to demonstrate now how exactly can one go about this. So now you're given a function here, and they are saying, show that this function that we have here is surjective. So how does one exactly prove that a function is surjective? So every time when you want to prove that a function is surjective, first you have to go to the original function and pay attention to the right-hand side description of that function. You see that? So every time your focus must be there. So how you prove such a question, you proceed as follows. First, you suppose maybe some random element y is in the range of f. You see that? So this is how you proceed. So you suppose that some random element y is actually in the range of f. You see that? Then the next thing that you have to do, you have to now prove that this y can actually be written in this form. You see that? So if you can prove that this y that you have chosen, which lies in the range, can be written in that form, then you have actually proven surjectivity. You see that? So to prove that, this is how I'm going to proceed. So I'll now say, now what is y? So we can agree that this thing that is called y is actually the same as saying e to ln y. You see that? So y can actually be written as e to ln y, because this is actually a law of logarithm that you should know. You see that? So there is a law in maths which you should know. So the law goes as follows. That ln of e to a is actually equal to a. It's a law or a rule that you have to know in mathematics. You see that? Or maybe you can just grasp it as follows, that the natural log of e is just 1. You see? So that's what exactly I'm playing around with here. So this thing y can be written like that. The fact that y can be written in that format, it is all that we need to actually prove the surjectivity of this function, because this function that we have here, if you look at it, it is a function which sends real numbers to real numbers. So that's what additionally is given. It is a function that sends real numbers to real numbers. So what I have to prove now is I have to prove that if y it can be written in this form, then definitely suggestion follows. You see that? So therefore I can now go on and say, therefore we can see that for all y in the range of f, they exist ln y, an element of the domain of f, such that f of ln y is equal to y. So this is how surjectivity follows. So you can see that it's really something that can really take time to get to absorb and assimilate on what exactly is going on here. You see that? But this is the logic behind the proof of surjectivity. So we'll do some more examples at a later stage when we've come to understand this concept a little bit more. For now, one example will just be enough, because a lot of manipulations that have to be used to prove surjectivity, they require someone at least with quite good experience in math. So for a first year course, we'll not try to bother much about doing a lot of problems on surjectivity. You see that? Then the last thing that we'll then talk about is bijectivity. What does it mean for a function to be bijective? You see that? So a function f which sends elements in A to some set B is said to be bijective if 1, f is injective, 2, f is surjective. You see that? So a function is said to be bijective if it is injective and surjective at the same time. So a function which is simultaneously injective and surjective is referred to as a bijective function. You see that? So which means if you are tasked with a question whereby you are asked to prove that a function is a bijection, you simply have to prove that that function is injective, and then secondly you have to prove that that function is surjective. So if you can prove these two for that given function, then the task is done. You can now make the conclusion that this is indeed a bijective function. Otherwise, we are going to end this session here. Try to solve more problems. Practice them and see if you can actually use these things that you have been demonstrated here to verify even more different examples that these are injective functions, surjective functions. If both happen at the same time, then you can also conclude bijectivity. Otherwise, thanks for watching, guys.